A mass tied to a spring is making simple harmonic motion with amplitude A around the equilibrium position. At what positions is the kinetic energy of the mass twice the potential energy? So, we know that the total mechanical energy of this object performing simple harmonic motion is the sum of its kinetic energy and its potential energy. And this potential energy is potential energy from the spring when it is like stretched out or compressed. And we know that the kinetic energy is given by 1/2 mv squared, 1/2 of the object's mass times its velocity squared. And the potential energy of the compressed spring or stretched spring is given by 1/2 times the spring constant k times the displacement x. And we're going to square that. And we also know that the energy is converted between these two forms as the object is performing this motion. So when it is compressed, let's say that the string is compressed here, all of this energy will be potential spring energy. And then when it reaches back to its equilibrium position, all of the spring potential energy from the compressed spring gets turned into the kinetic energy. And this is the equilibrium position. So when it is at equilibrium position, it's going to have the maximum possible kinetic energy and zero potential energy. And after that point, as it keeps going, it's going to stretch the spring, and in doing so, converts its kinetic energy into the potential energy of the spring. So the potential energy is greatest when the spring is the most stretched or the most compressed, and the kinetic energy is at its maximum at the equilibrium position as the mass passes through the equilibrium position. So knowing this, we can say that the total energy is also equal to 1/2 times the spring constant times the amplitude squared. And this expression is simply the maximum potential spring energy that's possible. So it is when the object is at the peaks for the simple harmonic motion. So you can also draw a simple harmonic motion as a wave, like this. So in this case, this here would be its amplitude. So this is its maximum displacement. And this axis is its displacement, and this axis is its time. It's the time elapsed. So it's going to look something like this. It has its maximum potential energy here when it is at the far points of its motion. So when the spring is most compressed or most stretched at an amplitude A, which is the maximum distance away from the equilibrium point. So that is that. And now that we have that established, we can actually fulfill our condition here, which is when the kinetic energy of the mass is twice its spring potential energy. So this equation simply becomes 1/2 mv squared. I should probably draw an arrow here. The kinetic energy is given by 1/2 mv squared, and the potential energy is given by 1/2 kx squared, where k is spring constant and x is the displacement. So this becomes 1/2 mv squared is equal to kx squared. And if you notice, we have a 1/2 mv squared from this equation, and we can actually substitute this back in. We can substitute kx squared back in for 1/2 mv squared when this condition is true. So we get that the spring constant k times the displacement squared plus 1/2 of kx squared is equal to 1/2 times spring constant times a squared. Now all of the spring constants cancel out. This becomes 3/2 x squared equals 1/2 a squared, where a is the amplitude. And these cancel out. So you get that x squared is equal to a squared over 3. And now we can take the square root of this to get that x, or the position, is equal to a, there's actually a plus minus since we're square rooting it, so a over the square root of 3. And the plus minus is used to symbolize that there are actually two positions where this could happen. And this is how you would solve this problem here.